It's my pleasure to present this wonderful work on progressive and efficient verification for digital signature. That's the result of a joint collaboration with Cecilia Boschini, who is a postdoc at Technion in Israel, and Dario Fiore, who is an associate researcher professor at IMDEA in Spain. Good. So to get everybody on the same page, let's see what the digital signatures are. Digital signatures are a cryptographic primitive that entails usually at least 3 algorithms: a key generation, a signing algorithm, and a verification algorithm. And signatures are used in many different applications. They are more and more used in smart cities and smart context, like smart light bulb. You might be able to let the light turn on when you are at home, but not when a thief enters your home, let's say. So you want to authenticate who is entering, or like authenticating who can unlock a smart bike or an e-bike, and not to mention all the authentication we need in connected cars and so on and so forth. What this talk will deal mostly with is the verification part of a digital signature. So in standard occasion, you get a public key, a message, and a signature, and you get an answer 0 and 1. What we are interested in is looking into the verification, the code of a verification algorithm, and we wonder what happens if there is an interruption while the algorithm is executed. And this interruption could happen because maybe we don't have enough time, or we are a resource-constrained device, we are running out of battery, we don't have enough space to store things, we have a shortage of whatever resource. So the first question that we will try to address is, okay, assuming I don't have enough time or enough resources, is there a way to speed up my verification process so that the time that it takes to complete the verification becomes short and the chance of an interruption, of course, decreases? And to do that, to devise a completely new verification algorithm that is more efficient than the existing one without any other assumption would basically imply having a more efficient verification than the one that has been studied for years. So we want to do that. Instead of generically, we say, okay, we allow a one-time setup. So one time you might do some computation, but then you enjoy a very efficient online verification. And the question 2 is, okay, suppose that I don't want to leverage a one-time setup. Is it possible to design an alternative way to perform the verification of a signature so that I progressively build confidence on the validity of the signature? So even if I'm interrupted, even if I can only execute my verification algorithm partially, I can say, I'm 100% sure the signature is incorrect, or I think the signature is correct with this confidence. So this is the setting of the work that I'm presenting. Now the outline of the presentation is, I hope I gave you a motivation for what we have done. Next, I will talk about what is efficient verification. I will start with an intuition, give you the syntax and the model, and then present a construction. And since I guess the audience is mostly cryptographers, I also would like to walk you a little bit through the core ideas of the security proof. Then we move to progressive verification. Also there an intuition, a model, and a construction, and then some final conclusion. It's okay to interrupt me, so please do that. I really like to have a dynamic exchange of idea and presentations, so feel free to stop whenever you have a question. It's better to address it immediately instead of 1 hour after the talk. Good, so let's move on. Whenever you see this light bulb, it's basically an intuition. So let's give an intuition of efficient verification. We have already seen this picture of the verification algorithm that takes an input, a public key, a message, and a signatures, and returns 0 or 1. Now, the idea of efficient verification is, let me run a potentially computationally expensive offline verification algorithm that only needs the knowledge of the public key, which is a public information that everybody holds anyway. And this offline verification will output something that I will call a short verification key, SVK. And with this output, I can enjoy a very efficient online verification phase where I get a message and a signature, and I can very efficiently decide if this signature is correct or not. And the key idea here is that I can repeat the online verification as many times as I want. So I leverage a one-time offline setup to perform an online verification several times. Efficient verification. Okay, this is not discovering a new thing. It has already been done, the paradigm of efficient verification. If you've been in crypto for a while, you've seen this maybe in verifiable computation, homomorphic authenticators, and specific signature schemes. Here you see some reference. However, what is lacking is a generic formalism to do this, to deal with this. How can I have a unifying framework to decide how to split? And that's basically what we want to do. We want to have a general way to create the split, and especially the online efficient verification for a generic family of signatures. But before we do that, we need to clarify what does this mean. So what is the model we're working with? So the syntax is going to be, give me a signature scheme, so key generate on signing and verification algorithm. An efficient verification will be a couple of two probabilistic polynomial time algorithms, off var and on var, with the following syntax. So the off verification will take as input the public key and a value k. So k you can think is an integer between 1 and the security parameter lambda, but usually is 1, 2, 3, 4, 5. And it's giving you essentially the confidence level at which you want to perform your efficient verification. And then the online verification, which is the efficient one, that takes as input the output of the previous algorithm, so the short verification key, message and signatures, and says 0 or 1. Are you correct or incorrect? Okay, as I said, this k is the confidence level that I'm setting when I do the offline verification. And for correctness, essentially, I would like that for any confidence level I pick, the output, the online verification will accept any signature that would be accepted by the standard signature scheme, given that I have performed all the computation honestly. Okay, so what we are doing different from previous work on this in this area of efficiency is that instead of designing a new verification algorithm, we want to augment the signature scheme with this tuple of algorithms. Okay, a couple of key observations. So indeed, as I said, this is an add-on property. So give me an existing scheme, I can devise something that does efficient verification for it without needing to change the scheme. So you can still run the standard verification, and especially I'm not changing the signing algorithm. So if there is like some post-quantum secure scheme that is in use, I don't need to change that scheme. I can just change how my device runs the verification. And secondly, the correctness property essentially implies that whenever the standard verification accepts a signature, the online verification will also accept a signature. And whenever the online efficient verification would reject a signature, then the signature will also be rejected by the standard verification algorithm. Now, if I'm not running too fast, you might have noticed that these two implications are basically saying the same thing. So one is the negation of the other. And security essentially comes from the fact that the implication will also hold in the other direction with high enough probability. But I'm getting a little bit ahead of myself. Before going that, we are talking about efficiency. So how do we measure efficiency? We measure efficiency with concrete amortized efficiency. So the definition is a signature scheme with efficient verification realizes R0, E0 concrete amortized efficiency. I need to have these two parameters to measure it. If doing the standard thing, so sampling your keys, give me a pair of message signatures that verifies, there exists a minimum integer, non-negative integer R0, which is essentially the repetitions, and a real constant E, which I want to be as small as possible, such that the computational cost in whatever model you're considering of running the offline verification plus running the online efficient verification R times compared to the cost of running the standard verification R times becomes small. So just to give an intuition, what I'm doing is a ratio between two things. Now, if you suppose that the length of these rectangles is actually the computational cost, I want to say that basically running the efficient, so 1 time the offline verification and 2 times the online verification should be computationally less expensive than running the standard verification twice. Twice is the example for R equal 2, and in this case, E is going to be like something like 0.8 if you measure the length, or 95. So what we are interested here is like the lower the value of R0, the sooner our technique achieves amortized efficiency, and the lower the value of E0, the more efficient the verification is with respect to the standard verification. Good, is the intuition clear? Then let's move on to the security model. So the security model is based on chosen message and verification existential and forgeability experiment. And it has the usual settings. So given a security parameter lambda and the confidence level k and a probabilistic polynomial time adversary, the probability of winning a certain experiment should be negligible. And the experiment looks like this. Now, I don't expect you to read this experiment, but let's have maybe a more human-friendly representation of the experiment. We're going to have a challenger and an adversary. Existential and forgeability under chosen message attack. It's the standard security notion for digital signatures. And it's basically the following. It says that the challenger that knows the security parameter lambda and the digital signature scheme sigma will sample a pair of keys. So it runs the key generation algorithm, sends the public key to the adversary. Then the adversary can run a bunch of queries to the signing oracle by submitting a message and getting back the corresponding signature. And finally, at the end of the experiment, the adversary is asked to produce message signature pairs, these red ones, mu star, sigma star, and it wins if the verification algorithm of the digital signature scheme outputs 1, and the message is not among the ones that has been signed by the challenger during the game. This is the standard notion. What we do here for the efficient verification, we add efficient verification queries. We let the challenger know the sigma, so the digital signature and the way we want to implement efficient verification. And the challenger also needs to know K, which is a confidence parameter that I choose when I run the offline verification. In the key generation phase, the challenger also runs the offline verification algorithm and produces this short verification key SVK. The adversary has the signing query phase as before, and in addition, it can also interact with the online verification algorithm, which will use the secret verification key on the given message and signature pair, and will return, do I accept or reject this signature? The output of the adversary is the same as before, a message and a signature pair, and the winning conditions are very similar. So we have that the adversary wins if the online verification outputs 1, and the message is not among the ones that have been queried during the querying phase, because then, of course, the adversary holds a correct signature, which is the one output by the challenger. But there is an additional condition, which is we want the standard verification would reject that signature. And the reason is, if the standard verification would accept it, then how can I expect an efficient verification to identify more forgeries than a standard verification? So if the standard verification accepts the signature, then I expect also the efficient verification to accept it. So the only discrepancy is going to be when the standard verification would reject, but my efficient verification is fooled by the output of the adversary. Good, then let's see how to do that. There are a lot of digital signatures out there. There are some based on prime numbers, like RSA, some based on discrete log and elliptical cryptography. But what we look mostly here is the post-quantum secured digital signature schemes. And the reason is that these usually have fairly heavy, fairly large keys and fairly computationally heavy, I say, verification with respect to others. And in particular, in the post-quantum world, we are interested in digital signatures that have a verification that has more or less this structure. So there's going to be a matrix that maybe depends on the public key, on the message, on a combination of these two, and a vector, which might be the signature, the message, some information like that, and equal to 0. We can always put it equal to 0 by, putting everything on the left of the quality. So this seems maybe very simplistic, but it's actually, we actually have a number of digital signatures that are lattice-based that have exactly this structure or can be turned into this structure for the verification. For instance, Gentry, Piker, and Bankutanata of 2008, and also more modern ones with the multi-key homomorphic authenticator in 2016, and so on. And we also have some multivariate, some digital signatures based on multivariate equation that meet this matrix vector and this style verification. So what I will show you next, which is our compiler to obtain efficient verification, actually applies to all of this. And in particular, I want to highlight Rainbow, which is one of the finalists of the NIST competition. Okay, so how do we build MV-style efficient verification for MV-style signatures with MV-style verification? Well, first of all, let's see an example. The verification here. On the left, we showed our generic framework for MV-style verification. And on the right is an example, the Gentry-Piker-Mancutanata 2008 paper. So we will start by having 2 bits, both set to 0 in the beginning. We will parse a public key. Now I'm reading the verification on the left side. We do some checks. For instance, if you look at the checks for the GPV, these are going to be simply that the vector that I'm getting is has a small norm, which is standard when you deal with digital signatures on lattices. Then we can have a get MV procedure, which essentially gets this matrix M from the public key and gets the vector V, in this case, from the message and the signature. And then you can see that on line 5, we are doing this matrix vector multiplication, which is our second check in the verification. And we will return 1 only if the signature has both passed the shortness check on line 3 and the check on line 5, which is this matrix vector multiplication.
Elena, we got a question.
Yep, great.
From Mukul Kulkarni, he is asking you, is there a strong variant of this security definition where signatures are also added to the list maintained by the challenger? And do your results extend to this strong notion?
So the strong unforgeability instead of existential unforgeability?
Yeah, I think so. Yeah.
Yes. Yes, we can turn our, sorry, I just missed the beginning of the question, but if it's strong unforgeability, yes. I just present existential unforgeability, but our model extends to strong unforgeability as well. We have that in the paper.
Thank you.
Thank you for the question. Okay, so what I want to highlight here is like the way we get M is basically just by padding the public key with an identity, so nothing too fancy. And that's on line 5 is the matrix vector check. Good. Now, even if you didn't understand the previous example, I can still give you an intuition of our compiler, and most likely you're going to understand it. So this is like my matrix vector multiplication, and hopefully I convinced you that there is a generic way to read many digital signature schemes in this shape. The intuition here is like, if I wanted to save up on the computation, I could check a number, let's say K, of rows of the matrix that I pick at random. And if there is a forgery, maybe some of them will be correct, here highlighted in red, but some of them might be wrong. Here, for instance, the second line that I'm checking would be red, so that will be wrong. So if we just do things this simply, we get to check K rows instead of N, but the unforgeability degrades quickly. So I can no longer make so sure to be unforgeable, because I might be checking the 3 rows where actually the adversary has embedded a forgery. But if I check the 4th row, it wouldn't be like that. So we want to be a bit more clever than this simple approach, but you don't need to be that much more clever. So the idea is like, if you give me a matrix, I can multiply on the left this matrix by a random vector and get a vector Z, which is a random linear combination of the rows of the matrix M. This means that Z in itself, information theoretically, contains information about every row of M. Now, if I check Z against V, I get only one element in the mod Q, but the probability of this being, in passive verification when V is actually a forgery is very small, because it contains information potentially from all of the rows of M. So if there was one row of M on which I would identify, for instance, the second one in the top example that is red, so that one is wrong. If C is 1 in that row, then Z will contain information about that row of M, which means most likely I won't get equal to 0, as I would expect. And even if I'm not convinced just by one, well, I can repeat this for a number of C's. So I can create a number of random, short random vectors, multiply them by M, get Z and Z prime. And the nice thing is, like, I can still do K checks, but instead of using the K plain rows of M, I'm using K vectors Z that are obtained as linear combinations of rows of M. But the unforgeability here doesn't degrade too quickly because it comes from the randomness that I embedded in the C's. So it's actually degrades exponentially. We will look more into this in the security proof, but this is the whole intuition of our compiler. We are basically creating a random linear combination of the rows of M and then checking that V is equal to 0 against this random linear combination. And the Z is what we called SVK before, so this short verification key. And it's short because I'm going to have K of them, where K is my confidence level, instead of N, which is the number of rows in the matrix M. And just to give you an intuition, usually M runs around 100, 200 in implementation of lattice-based signatures. So it's not a small number. Okay, this is how our compiler looks like. I don't expect you to read everything in detail. If you want to do that, please check the paper. It's available on ePrint. But I just highlight this part, that it's the code, pseudocode of what I did before. So sample a random C, multiply it to the left by the matrix M, get your random Z, put these Zs that are linearly independent together and construct the short verification key. And then for the online verification, I will have to do the standard check. For instance, the signature is short when I do with lattice-based signatures. And then I will simply do this check. Instead of having a big matrix M, I'm going to have each row of Z multiplied by V. Okay. So what is the concrete amortized efficiency if we use our compiler? So I hope you remember this picture from before. So this is the setting we are doing now. I have the offline verification that I do it once, and then a bunch of online verifications. Well, if it all depends on the value K. So for this table, we chose K to be such that the probability of the adversary to produce a forgery is 2 to the minus 128, at least. So it's unforgeable in the standard cryptographic sense. And then we compute the minimal K for which that condition is met. And from there, we get the concrete amortized efficiency. So what is interesting here is if you look at the first row of the table, you see that for construction where Q is exponential, which are, for instance, the homomorphic signature schemes cited over there, we get, let's say, the highest level of confidence already with K equal 1. So instead of checking a whole matrix, I could just check one row that is obtained as a random linear combination of the rows of the matrix. And so I get the concrete amortized efficiency already for R0 equal 2. And my concrete efficiency is 0.51, which means that the online efficiency, so the computational cost of the online verification compared to the computational cost of running the standard verification is less than 0.4%. So the efficiency is like super efficient. It costs only 0.4% than the standard verification. But these are very specific schemes. So the signature schemes are homomorphic. So let's look at standard signatures. And this is the case for the Boolean signature, GPV, and MP. In this case, Q is smaller, so it's 2 to the 30. But we obtain the same unforgeability if we set K0 equal to 5, so the minimum confidence level. And in this case, the online verification becomes 2% of the cost of the standard verification. So I can achieve the same soundness level by using only 2% of my computational resources in the online verification. And finally, for the multivariate equations for Rainbow, these are actually, I checked today, and they have set their parameter even higher, which, whatever they push up is better for us. But these were the estimate of 6 months ago, and we get 50%. So our online verification is going to be 50% less expensive than, or it will cost only 50% of compared to the standard verification. Any questions so far?
How do you compute this confidence level K0? How do you
that
say
will come in the
this?
security proof, which is exactly the next.
Okay.
Great question.
Thank you very much.
This leads me to, okay, how do we get K? Well, K depends on the security, right? And I told you the security game, but I didn't tell you how I prove security of our compiler. So here it comes. Our statement is that give me a signature scheme with style verification that is existential and forgeable. If you use our recipe, our compiler, you get a signature scheme with efficient verification that is it's essentially unforgeable under chosen message and efficient verification attack. And the advantage is the following. Where to give you an intuition, this Q to the K, Q is the modulus of the algebra structure we are working on, and K is this confidence level. So you will see that, like, I will choose this case so that the advantage becomes, 2 to the minus 128. And QV instead is the number of total verification queries that we are doing. And it's usually polynomial and way, way smaller than Q to the K. Good. So let's give an intuition of how the proof works. Do you remember this image? So we have the MV style verification, great. And then if you remember, we did this trick. I multiply to the left my matrix M by a random matrix C and get the short verification key Z, sorry. And then the verification would be, I take the Z against the vector V and I want to see 0. Great. So that was my offline verification, computing the SVK Z. And then my online verification is checking essentially each row of Z against the vector V. So we have the following observation. Because Z is obtained by M, whenever MV is 0, also ZV is 0. Because Z is nothing else that's a random combination of M. So if M is 0 against V, then ZV must also be 0. And the intuition about the security is that the implication holds also the other way with high enough probability. And this high enough probability is what we are checking now. Okay, so remember the winning condition of the game. We have that the adversary is outputting a message signature pair, mu star, sigma star. The online verification should return B equal 1, so should accept it. The message shouldn't be queried to the signing oracle during the game. And the online verification, the standard verification should reject the signature. So let's see what happens. If the standard verification gives me 1, then the online verification has to accept because it's obtained from the standard verification. So there is no leakage of information here. If the verification accepts and the online verification reject, this is impossible to happen. And if you remember why, it's because Z is obtained by M. So you can write Z as, CM in a product V. So that's impossible for correctness. But what can happen is that the standard verification rejects, so outputs 0, and the online verification outputs 1. And this is precisely what we call the bad event, and what I will give you the estimation in the next slides. And the final case is when both of them would reject the signature, but in a sense, there is a sort of leakage. And the leakage is the adversary will learn that certain rows of the matrix M appear in Z. Are there questions?
Yes, there are questions. Can you see them, Elena?
I don't see them. I just see that
okay.
The number of Q&A is higher. So
yeah. So it says, is Q the number of queries by the forger? And can you please explain why higher Q gives better efficiency?
Yes. So great question. Q is not the number of queries. That's going to be QV. Q is the size of the algebraic structure we are working on. So if you think of lattice, Q is the Q used by the lattice. Usually Q is 2 to the 80, more or less, like a prime on that size. So that Q is not the standard Q. We will call the number of verification queries QV. Yeah. Was that all? Yes.
Yes,
okay.
that was all. Yeah.
Okay. So we don't need to worry about the first and the second line of this table. The third line is our bad event, and I will call the other the non-bad event. So there is still some leakage. The adversary learns that some rows of Z are not in the left kernel of the forgery V that it has produced. Good. So here I'm just restating what the event bad I means. Bad I means that the standard verification would reject the message signature pair, but the online verification would accept it. So that's what we don't want. And this is just to have the picture of how we build things. So I have Z and V, but Z is actually C times M. And for convenience, we will call MV a vector W, and we just check C times W. This is just mathematics. These things are all equivalent 100%. It just makes the analysis easier. So with this new notation, C and Z, if I reuse them, leakage happens in two cases. Here I'm a bit repeating what was in the previous slide just to make it extremely clear. If bad I happens, then I have a forgery. On verification is accepting something that the standard verification would reject. And if not bad I happens, then the online verification rejects a query, but the adversary learns what rows of the public key are used in my secret verification key. So by doing a union bound, I can actually upper bound the advantage of the adversary with the following formula, which intuitively says is counting the first time that a bad I happens. So we are basically in the stronger forgeability sense here. Like if I see a forgery, then I can reuse it and win the game. And then I assume that up to now, all of the previous queries I've done were actually of the type non-bad, which was the only other way I could leak information, because we saw that the other cases didn't leak any information. So this is an upper bound on the adversary's advantage. And how do we give a number to this? And to connect to the question that we got before, here you have the QV, which is the number of queries, verification queries that comes into play. So you can see it in the top of the sum. So
we got
important
questions.
Okay.
Eduardo Soria Vasquez, he's asking us, hi Elena, what are you presenting is in the case when you are on a finite field, right?
Yes.
If for example was a power of 2 and you were working with the integers modulo Q, the probabilities you gave a couple of slides ago should be different.
Sorry, if Q is
was a power of 2.
No, that's the size of the
and you were working with the
if you are referring to this, yes, I write Q is 2 to the 30, but that's its size as a prime number. So it's going to be a prime number. It's the size of the lattice structure we are working with. So it should be like a tilde there. So of that size, magnitude, sorry, of that magnitude, but it's not 2 to the 30.
Okay.
It's okay. A prime number that is of the size of 2 to the 30, but it's not the number 2 to the 30.
Yeah.
But yes, we are using the fact that we are on a finite field to prove the uniqueness of like the product being 0. So thank you for the comment. Okay. So this one is what we saw. Good. Okay, so a little bit of math here, which hopefully will address the questions that I got so far. So before the adversary does any query, all of the possible choices of C are possible. So my set calligraphic C is made of all of the possible matrices that are dimension K by N, where K is the confidence level, and we suppose that it's publicly known. And after I get I number of rejected verification query, then I know that this is no longer the whole set, but it must be a subset. And these calligraphic H's are essentially hyperplanes. I will explain in a second. So assume with a very much simplification that my C is a vector, then there's going to be an hyperplane of things that are orthogonal to this vector. And these are exactly the vectors on which the adversary does a forgery. So, but the adversary doesn't know which hyperplane this is, so he will try a W1 and find out that it's rejected. But this means that the hyperplane orthogonal to W1, the matrix C does not contain rows. It's not completely, the rows of C are not all from this hyperplane H1. And again, when I do another query W2, I know that if I'm rejected, then it means that W2 is not orthogonal to C. So the rows of C cannot all lie in the hyperplane that is orthogonal to W2. So by continuing like this, you can get an intuition that the more queries I do, the more knowledge I learn. And that's why QV comes into play in our advantage formula. So we just said that I can bound the advantage with the sum over QV, the number of queries that I do. And then inside the summation, I have this probability of bad I given non-bad ij. Again, the non-bad ij was the only case in which I had leakage. And now I'm looking at the first time that there is leakage, bad I happens, a forgery. So I argue that this happens, like this probability can be bound by above by the following expression. And the following expression, sorry, I screw up with it, yeah, is essentially this. So what I'm saying is like I have Wi on which C is equal to 0. This means that all the rows of C must be in the hyperplane orthogonal to Wi. And the size of this hyperplane is, of course, the number of points I have in an hyperplane of the correct dimension. And after I queries, I must have learned that not all initial set of Cs are possible, of possible matrix Cs, but this is reduced because the rows of C cannot all be taken by the hyperplanes Hj that I queried before. And just by a simple counting argument, it turns out that fraction, that ratio, can be upper bound by 1 over q to the k minus 1 minus I. And once we plug this into the summation, we get to the formula that we gave before. I know that I'm skipping some steps, but the steps are just standard math. So there is nothing hidden there. The reasoning is the interesting part. A small observation to do is also that this compiler is all information theoretic. So this proof is basically a geometric proof, and it's based on the randomness contained in the C. So we are not adding any additional, we're not adding any assumption, computational assumption to the ones that the digital signature has in order to achieve efficient verification. Good. So I'll give you the motivation. Now I talked about efficient verification. If there is any question, now is the time before we move to progressive verification. Nothing. Okay, progressive verification. Let's start with the intuition. So we have again our verification algorithm, takes the standard inputs and gives out a 0 or 1. What we want to do with progressive verification is to design an alternative way to run the verification process so that if it's interrupted at a certain point, I will get an information, sigma is valid, and accuracy. So how confident am I that sigma is indeed valid? I didn't have the time to execute my algorithm in its entirely, so I might be wrong, but I'm confident 80% kind of. So the way we will do this is essentially by describing a sequence of steps so that if the step gives a bot, I'm 100% sure that the proof is wrong. But if this step, let's say, accepts the proof, then I will move to the next step, which will tell me if this step fails, then I'm sure that the signature is wrong. But if this step continues, then I will be progressively build confidence and then end up with this alpha 3. So this function alpha will, increase the confidence I have in the validity of the signature. And what I would like is that the output of the standard verification should, more or less be the output of this progressive verification. So the progressive verification shouldn't reject things that wouldn't be rejected by the standard verification, but it should also not say, oh, this signature is correct, and I'm 100% sure when the signature is not correct. But it might happen that this says the signature looks correct, but I am only 10% sure. I only could do a little computation. Okay, so let's look at the syntax. We're gonna need a couple of things. We will need a T, which is the maximum number of steps that we allow in the verification, progressive verification, and this alpha, which is my confidence. And we define T alpha progressive verification to be a stateful probabilistic polynomial time algorithm that has the syntax at the bottom of this frame. So essentially, at the beginning, my confidence is nothing. And of course, if you ask me to do T step where T is less than 0, I will still say nothing. If you ask me to do T step where small t is bigger than the number of steps I have, I will set it to my biggest number of steps. And then for j, that goes from 0 to all the steps you allow me to do. So t is this interruption parameter, you can think about it. I will run a program, my progressive verification step of level 1, 2, 3, 4, t. And if the progressive verification steps returns 0, then I say the signature is wrong. Otherwise, I'm upgrading my confidence to a higher level of confidence. And it's important that this progressive verification is stateful, because we will update the state and carry on what's it called? Our efficiency, make the model as general as possible, having the state. So of course you can make it stateless if you replace the state with empty, which was done by other people before, but having it there makes it possible for us to combine both progressive and efficient verification, as I will show you in a second. And for correctness, we want that whenever the verification outputs 1, then also the progressive verification should accept with the highest accuracy level given by alpha. Again, the security will prove that these two verifications behave equivalently with high enough probability or with overwhelming probability. The security model. In the security model, there is actually a twist, because now we allow the adversary to pick an interruption parameter t star. And of course, if you let me do very, very little steps, I might be wrong in assessing a signature. So we need to keep that into account. So the existential unforgeability for progressive verification, we let the challenger know, as usual, the security parameter, and the progressive verification implementation will generate keys, give the key to the adversary. Now the adversary will run his usual signing queries, and also the progressive verification queries at different interruption parameters t. In the end, it will output message signature and an interruption time t star. And he loses the game if the message signature t star are rejected by the progressive verification, but it wins if it's not rejected and the message has not been queried before, and the standard verification again would reject it for the same reason as the efficient verification. We need that clause. Okay, good. Let's see how to realize this thing. We start again from the same intuition as we had before, MD style verification. And we start actually from the same compiler we had for efficient verification. And what we do is very simple. You can say, okay, now my offline verification is going to be my step 0, which gives me accuracy 0. But then if you let me do step 1, I will actually check the first row of Z, which gives me accuracy 1 over Q. And if you let me do more and more steps until I get to the last one, then I will get accuracy 1 over Q to the K, because all of these rows are chosen independently, are obtained from C, that are sampled independently. So they build on the randomness. And this also gives an intuition on how to get progressive and efficient verification at the same time, because now you see that the offline verification is a multiplication of 2 matrices, so it's fairly computationally heavy. But if I can offload that to the offline verification, and then I can do a progressive online verification, then I get something very cool, which in particular lets the verifier set the soundness level at which he wants to check the signature, because I can decide I want to check it for, I don't know, 3 steps for a specific signer. And I'm okay with the soundness error of Q to the third, Q to the -3. Okay, takes away from this talk. The online-offline verification paradigms apply to standard verification too, and not just to specific kind of verifications. Cool. There exists an information theoretic compiler, a transformation that I showed you, that allows any MD style verification to be turned into an efficient verification. And this information theoretic transformation can also be used to basically obtain progressive verification in a black box way for MD style verifications. And our transformation compilers do not require one to change the original signature scheme. So previous approach to obtain efficient verification or progressive verification would design a signature scheme that is completely new. So with a new signing procedure that would create a signature that is progressive verifiable. But we want to say, okay, what can we do with the signatures that are already there off the shelf? Other implication and future work is to study a little bit better how to combine the notion of progressive and efficient verification together, especially when there is leakage that might happen by being interrupted early and having a higher inaccuracy. Progressive verification can be used to intentionally adjust the security of according to the capabilities of a device. For instance, if I'm running out of battery, I might be okay to just check signature at a lower accuracy level just to make my device last longer. And it would be interesting in the future to find transformation that apply to different mathematical structures. So as you've seen, I work very much with matrix and very simple geometric intuitions and the fact that we're working on finite fields. But what happens if I want to do the same on finite groups or on isogenies or whatever other structure is there? And finally, yeah, it would be nice to, or actually, it's my next step to investigate. All of this talk has been on signature verification, but what happens if I want to apply this technique to commitment schemes, ARCs, other verifiable computation? Do we get progressiveness also in those fields? What does it mean to have a progressive? Will people be okay to, reduce the soundness level, trade some computation, some security for less computation, and so on? Good. So that's bringing me to the end of my talk. I hope it was understandable. It's so strange to do talks via Zoom. But I welcome any questions.
I know it's kind of strange, but you got a lot of questions. Thank you very much for your very nice presentation, by the way, Elena. We have one final comment from Mukul. He's saying, great talk. Thank you very much. Is it correct to say that we gain this progressive and efficient verification by replacing public verification with designated verifier? Are there any works which also have public verifiability?
Yes, it's a very insightful way of putting it. It becomes designated verifier, but in a sense, the signature doesn't state who the verifier is. So you're basically twisting a publicly verifiable, you take a publicly verifiable scheme and make an efficient version by having a secret verification. But it's not necessarily designated verifier. So everybody can check the same signature with a different secret verification key. Yes.
And is it possible to get public verifiability if we settle for computational reduction than information theoretic?
Yes, so that's actually a very nice caveat. So if we were able to design a verification that is publicly verifiable, and it's faster than the existing verification, it means that we basically have an improvement on the efficient verification of a given signature scheme. And it's harder to do than with the secret, than sampling secret randomness. And the reason is essentially you're boosting the pick dilithium, pick GPV, pick all of these signatures. They have been studied for so long by so many people and improved to the best they can. Now, you cannot go much further. You cannot improve much better a matrix vector multiplication if you don't do some tweaks. So, and the tweaks is you need to sample some secret things. Otherwise, if everything is public, you can, I would be very impressed if you can do anything better than what these people have been doing for so many years.
Okay, thank you very much. In the case of, I have a question, Elena. In the case of progressive verification, so for instance, some entity can say, I just want 50% of certainty instead of 100%. Why? What would be the reason for that?
Okay, I'll give you two reasons. First reason is, actually three. First reason is I'm running out of battery and I want to be able to check more signatures, saving up battery. Second reason, I actually don't have enough space in my device to store so many rows. And that's, for instance, the case of some IoT devices. So maybe I can store a few hundred bytes, but I cannot store megabytes of public keys. So I have a crop, I have an upper bound on which I can do. But thirdly, imagine a distributed verification setting. So I have a network of nodes that I kind of trust. Everybody's sampling their secret short verification keys. And I can only check one line because I trust that all other 100 people around me are checking one line. And if one of them would find a forgery, they will, speak up. So there are many ways in which you can say, I can actually boost, either I cannot do better than this, or I just want faster. Like imagine that you are driving a car and you want to have still post-quantum security, but you also want to be able to take decision very quickly. Then maybe you're okay with a slow threshold, and then slowly you improve on the correctness, on the accuracy of your decision. But you want that if this decision looks wrong, I want to be able to interrupt immediately. So you can actually twist it as a very early detection of, bad things. The standard verification you need to go until the very end. And with the progressive, if you have a failure, you can get it on step 0. And then you don't need to do the whole computations, which is very important in time constraint settings.
I see. Thank you very much. I also had a doubt on the offline verification that you mentioned. Yep. The output of this function is secret, is private, right?
Yes, it's private and known to the. Oh, let me find a slide. Yeah, maybe this one. The offline verification, then probably. Yeah, so the output of the offline verification is going to be this Z, which is a secret verification key. So, and that's private.
My naive question is why is private? Cannot be shared by 2 or more users?
Oh, it can be shared by more users. It just should be private to the adversary. For the same reason as, I'm sorry, I don't remember the name's question on why can't I have public verifiability and efficiency at the same time. Public verifiability and progressiveness, that's doable if that was the question, or like if that could be a twist answer to that question, it's doable, but so far it requires one to devise a specific signature scheme. So I will design a signature scheme that signs in a special way so that it allows a special verification that is progressive. While what we want to do is how can I get progressive without changing the scheme? And the way we devise is with the secret verification key, but progressive verification might be possible in a public setting, yes. Not efficient. I doubt efficient is possible.
Okay, thank you very much. I don't see further questions, Elena, but you have plenty of them. So thank you very much again. Thank you for accepting our invitation. It was a very insightful presentation, and we have learned a lot. And thank you for the nice presentation, very nice effects, okay. As usual in this case.
Thank you, and thank you for the invitation. I hope it was clear. I maybe spoke fast as usual. You can find more information on the ePrint version of this paper, and my email is probably floating around or is public information, so feel free to reach me if you have any further question or if you are interested in going into any of the future direction. I'm happy to collaborate.
Okay, I have one final comment from Eduardo.
Yep.
From Jorge Saab, he's asking us regarding the distributed verification. You just mentioned if one node fails to verify the signature, is there a way for it to easily convince the others that the signature is
super
wrong?
Efficient. Yep. So the way is he will post his row of Z for which the signature doesn't verify. Everybody can do this inner product and check that it's not 0. And then the proof is going to be, this is the randomness of C that I sampled to create that row that proves that the signature is incorrect.
Okay.
But from here to actually have it as a full-fledged distributed verification scheme, there is a couple of more tweaks when it comes to security that you need to be aware. Like, for instance, you need to be able to make sure that whoever, like that there is a broadcast channel that a person can, it won't be shut off if the node verifies that checks that the signature is incorrect. It needs to be able to broadcast to everybody. So there are a few tweaks there.